Moving up.
Right, but I won't be back by that time. Yeah,
Okay, guys, let's welcome Professor Petta from Physics Department of Princeton University. And the lecture of this title is Semiconductor Quantum Dots. Please.
All right, good morning, everyone. Hope you've enjoyed the school so far. I'm going to talk about device physics and namely how we can control the spin degree of freedom in systems that are called semiconductor quantum dots. And this first lecture will be a mix of review and some new results from my research group, but a lot of people have contributed over the past 10 years to the development of quantum dot devices here in my research group. And I just want to acknowledge the people who have done the work, and you can see many of them have gone on to really great places and are continuing their careers elsewhere as postdocs. So the first lecture, I just want to give you a brief overview of quantum dot devices and spin qubits. And so I want to try to describe to you how we can isolate single electron spins in a semiconductor heterostructure, and then walk you through the basics, sort of go through each step of the DiVincenzo criteria and show you how we can initialize a spin in a well-defined quantum state, read out a spin to determine whether it's spin up or spin down, how to control a spin coherently. And so if you want to dig into the details, these are really good references going back kind of 10, 15 years that cover the basics of the field, quantum dot devices, spin qubits. And this more recent review of modern physics is focused on silicon-based quantum computing. So it's kind of more up to date. Okay? But these are nice resources for learning. And then in the second lecture this morning, I'm going to talk about cavity QED implementations with quantum dot devices and light matter interface. So we're going to take these quantum dot devices and place them inside of high quality factor cavities that allow us to interface a single electron with a single photon. And the goal here for this research is to be able to couple single qubits to single photons for long distance transfer of quantum information. And just earlier this year, we demonstrated that we could do this coherently, that we could coherently couple a single charge and a single photon. And what we're working on in the lab right now, today, is trying to couple a single spin to a single photon. And you'll hopefully appreciate by the end of these two lectures the advantages of spin, if Steve hasn't already convinced you. All right, so here's where we're headed for this first lecture. Just want to make sure we're all on the same page, but I want to introduce these devices. These are called quantum dots. They allow us to isolate single electron spins in a semiconductor environment. And then we'll briefly discuss the physics of why this is possible. Normally we think about controlling bulk materials where we have large number of electrons, and you think about K-space, but this is a very different regime where we're going to have one electron and we're going to control its properties. And so we need a way of actually measuring charge states. I'll talk about single charge sensing, and then we'll transition to the spin degree of freedom. Now that we have an electron trapped in a semiconductor heterostructure, we want to look at its spin. So we'll turn on a large magnetic field so that the spin states of that electron spin up and spin down, Zeeman split by the Zeeman energy. I'll show you how we can measure that Zeeman splitting and then do some tricks to actually control single spin states coherently. And then toward the end, I'll talk about results that we just submitted earlier this week, new results showing that we can implement a quantum CNOT gate with electrons in silicon by applying a single electron spin resonance pulse to a 2-qubit device, okay? And this is a summer school, so you should feel free at any point to raise your hand and say, Jason, please slow down, cover this in more detail, or I'm bored, skip to the next slide. But we can dictate the rate here as we go through the material, all right? So first off, what is a quantum dot? What we want to do experimentally is make a platform in the laboratory that allows us to isolate a single charge or a few charges. And ideally, this would be in a controllable system so that we can control the charge wave function and eventually the spin degree of freedom. And so there are a number of ways to do this. Basically, what we want to do in the laboratory is build a cage around a single electron and trap a single charge in space. And ways to do this include taking single molecules and placing them between two electrodes. This is a field called molecular electronics. You could also imagine using chemical synthesis routes. It's possible to make metallic nanoparticles. These are gold nanoparticles here that have diameters that are on the order of 5 nanometers, but there's some number of electrons on these nanoclusters, and there's confinement, right? Because there's a vacuum outside of the particle. So the electrons that are sitting on these gold clusters are basically trapped there. And as a result, you can actually resolve discrete particle in a box states in a system like this. Since we want to have a quantum system that we can control, it's actually very convenient to work with semiconductors where you can use gates to tune the electronic density in a material system and actually do that on a fast time scale. Here are 2 examples of different semiconductor quantum dots. This is a picture from Seigo Tsurucha's group of a vertical quantum dot. And you can imagine if you want to get down to a single electron regime, you take a lightly doped piece of semiconductor and start chopping it up into smaller and smaller pieces until you just have a very small region of space that contains a few electrons. And that's basically what they did in this structure. This is an etched pillar. You can see here's a pillar of gallium arsenide, aluminum gallium arsenide, and they've used this vertical quantum dot structure to make an etched quantum dot. To have more control, instead of etching a system, this is a commonly used approach that's called a lateral semiconductor quantum dot. But basically, you can start with a 2-dimensional electron gas system, and on top of that heterostructure, fabricate gate electrodes. So these are titanium gold gate electrodes that are sitting on the surface of this heterostructure. And by applying the appropriate voltages to these gates, you can basically create a corral that you can trap a single electron in. So these are lateral quantum dots, and what's powerful about the lateral quantum dots is it's not etched and kind of permanent. So you put these gates down, but you can always adjust the voltages on these gate electrodes, and that's what gives us tunability over these systems. So in most of the experiments today for charge and spin qubits and semiconductors, they're based on this approach of having some kind of gate-defined potential that the single electron's trapped in. Okay. So it's just an overview of different ways of doing this. And there's actually, this field has come a long ways. I just had a workshop earlier the week in Finland, and there's a group in France that's shown that they can take a cluster like this, place it between 2 electrodes, and coherently control the electron and nuclear spin state of that cluster. The kind of difficulty with this approach is typically the yield is quite low when you make devices like this. So they measure 100 devices and maybe 1 works because you're trying to control a single molecule. These are much bigger. If you look at the scale bar here, this is about a micron across. So we make devices like this in the basement. They're made lithographically. They're big enough that you have enough control over the quantum state. Whereas, this is a very small scale device with just a few angstrom gap here between these gate electrodes. Much more difficult to make.
Excuse me?
Yes.
In the lateral construction,
Yeah.
How large is the scale the electrons are really confined?
Yeah, so this is a huge device in comparison to the Fermi wavelength of gallium arsenide, which is about 30 nanometers. This is an old SEM image from Charlie Marcus's group, and this quantum dot probably has 100 or 200 electrons in it.
I see.
I'll show you newer devices where we really get down to 1.
Okay.
They're much smaller and they look very different than this.
And the real region, the electrons are confined about several nanometers?
It's on the order of, right, so there are a couple of things that are important. These electrons are in a semiconductor,
Yes.
and from solid state physics, there's effective mass,
Yes.
and the G factor can be different. So the effective mass of electrons in gallium arsenide is quite small. It's about 0.06 times the free electron mass. And that means that the Fermi wavelength's on the order of 20, 30 nanometers.
I see.
And so to make a box for an electron in gallium arsenide, it's about that big. You know, it's tens of nanometers across. It doesn't need to be a single nanometer kind of box size, right? So that's how you can leverage the properties of semiconductors to actually make practical devices at the single electron level. Good? Okay. This is before my time. These are older devices looking at very different physics, but now you can get down to one electron. All right, a lot of times quantum dots are called artificial atoms, and here's a short list of reasons why. For a real atom, right, we have electrons in orbit around a positively charged nucleus. What we're doing with semiconductor devices is we're making a gate-defined confinement potential that's much more extended, okay? So it's lithographically defined. You know that for atomic vapor, you can shine light through it and probe the absorption or emission properties of a vapor cell and resolve discrete electronic states of atoms and molecules. For these kinds of quantum devices, what we can do is measure the current or conductance through the quantum dot, and we'll actually be able to probe the local electronic density of states. And we can resolve discrete quantum energy states in these nanofabricated devices, not by shining light through them, but by looking at electronic transport, by probing the density of states basically at the Fermi level of these systems. And you know that we can take individual atoms and combine them together to make molecules, and we can do the same thing with quantum dot devices. We can take two quantum dots, fabricate them close together so that there's wave function overlap between the two quantum dots, and that will lead to molecular bonding. And so you can actually see the formation of bonding, anti-bonding states in devices that are called double quantum dots. There's some important differences that are going to shine through in the physics today when we compare atomic systems to quantum dot systems. The first thing is size scale, and this maybe comes back to your question, but instead of trapping an electron in vacuum, we think about angstrom length scales for atoms. Our sizes that we make in the laboratory might be tens of nanometers. And so the box that we're trapping the electron in is much larger. That means that the particle in the box energy spacings are much smaller. So instead of having 13.6 electron volt spacing like it would for hydrogen, the energy scales in our system are usually on the order of hundreds of micro electron volts or a few milli electron volts, much smaller. And what that does practically, and you heard about this I'm sure in the D-Wave talks, is we need to work at low temperatures. So all of these experiments are performed at millikelvin temperatures in a dilution refrigerator so that there's very little thermal excitation of the electron up into these low-lying excited states. Okay, so this is a practical issue with both semiconductor quantum dot devices and superconducting devices where you have very similar energy scales, right? You have to work at low temperatures. Another thing that's important, and we just briefly discussed this in the context of effective mass, right? But this electron is sitting in a crystal, and that crystal has specific properties. And in the case of the 3-5 semiconductors, this electron that's trapped in our dot has an extended wave function. It might be over tens of nanometers, and it samples a large nuclear spin environment. There might be about 10 to the 5, 10 to the 6 nuclei that this electronic wave function overlaps with. And this leads to a more complex hyperfine interaction. In real crystals, the spin-orbit coupling is not a simple kind of L dot S Hamiltonian that you learn about for the hydrogen atom. This is a spherically symmetric confinement potential, but there are more complicated electric fields in crystals that lead to a material-dependent spin-orbit coupling, anisotropies, because a lot of times we're combining electrons at interfaces, so there are going to be specific directions through which the spin-orbit coupling is strong. And so there are a lot of complications that come about when we make the transition from atoms to these artificial atom quantum dot devices. Let's talk a little bit about how we actually build these in the laboratory. This is a picture from Sarah Cronenwet's thesis from the Marcus group. But basically what we're going to do in most of our experiments is we're going to make a quantum dot. We're going to trap a single electron by starting with a two-dimensional electron gas system. And this is a picture of what the heterostructure looks like. This is a stack of gallium arsenide, aluminum gallium arsenide, and these materials have different band gaps. Gallium arsenide has a smaller band gap than aluminum gallium arsenide. So if you dope aluminum gallium arsenide with electrons, those electrons will fall into this interface between the two materials. And you end up with what's called a two-dimensional electron gas. Many groups will just call it a 2-deg. So you can think of this 2-deg as a sheet of free electrons They're living in a gallium arsenide crystal. So these electrons have gallium arsenide G factor. They have gallium arsenide's effective mass, but it's a quasi 2D sheet. And the density is quite low. It's on the order of a couple times 10 to the 11 per centimeter squared. So this gives us a gas, and this electron gas has been used for decades here at Princeton and elsewhere, say by Dan Sui, to look at quantum Hall physics, fractional quantum Hall physics, and other 2D physics. What we want to do is isolate one electron in this 2D sheet. And the way that we do this is we'll take this heterostructure, and on the top of it, we'll use electron beam lithography to fabricate gate electrodes. Gate electrodes are just nanometer scale pieces of patterned metal. And the device that's shown here is something called a quantum point contact. It's one of the simplest structures that you can make. But what we're doing is we're taking this two-dimensional electron gas and we're making a constriction in it. That's the point contact. The point contact is the connection between one side of the two-dig and the other side of the two-dig is this narrow channel. And the way to physically think about how these devices work is that if we apply negative voltages to the gates that are on the top of this heterostructure, those negative voltages are going to cause the electrons in the two-dimensional electron gas to scurry away, right? There's Coulomb repulsion. And so that you can actually selectively deplete regions of this two-dimensional electron gas. And in the case of the quantum point contact, we're just forcing electrons to flow through this narrow constriction here. Okay, so that's kind of a simple starting structure. Well, how do we make a dot? What we do is instead of having two split gates like this that force electrons to flow through this channel, we want to build a corral, right? Kind of like a cage around the electrons in the two-dimensional electron gas. And again, this is before my time. This is like the mid-90s. Picture from Marcus group. Here's a scale bar. Instead of having two gates, there are about 6 gates here that are used to define the quantum dot. So this is the corral that the electrons are trapped in that form the quantum dot. And to probe the quantum dot, we're going to measure the conductance or the current flow through it. So there's a source electrode that electrons can hop onto the dot from, and there's a drain electrode that allows the electrons to hop off of the dot. And so you can basically measure the current through the quantum dot and probe the electronic properties of the system. We'll talk in more detail about how that actually works out in terms of energy level diagrams on the next slide or two. And what's happened over time is that these devices have gotten a lot smaller. This is a picture from Andrew Sakraida's group. There's a research group in Canada that's looking at dots, but they made the first single electron lateral quantum dot. This is a picture of the device. It's much simpler. It's quite a bit smaller, but they were able to get down to 1 electron occupancy. And also there's been a trend over the past 10 years to scale up in terms of number of dots. So there's been a scaling down in terms of number of electrons, from hundreds to just 1 electron on the dot. But also we can make more complicated structures. This is a double quantum dot. It's like a molecule. This is a triple quantum dot where there are 3 quantum dots that are coupled together in series, a series configuration. And then this is a paper from our research group from last year showing a 12 quantum dot device where we basically have 9 single electron quantum dots connected up in series. And to measure this device, we have 3 charge detectors that we can use to probe the local electrostatic environment. Okay, so this should just give you a flavor of what these kind of samples look like and what the state of the art is in the field.
Excuse me? In
Yeah.
the last picture, you don't have like that many electrodes?
Yeah, this is a picture of the electronic density.
Okay.
It's a simulation. And I'll show you, I think in this talk, if not the second talk, what the gate pattern looks like. It's actually on the first slide of the talk, I think. Okay. But this is just the electron density to give you a sense of where the electrons are trapped. For this device, you'd have a dot here, here, and here, kind of where the black circles are. Okay. Good. So let's talk about the physics. How do we actually measure these things? You can draw a simple circuit diagram for the device. Imagine that this is our dot. It's just a small puddle of electrons. And we want to couple to it somehow. So we're going to connect it to the outside world by 2 tunnel barriers. One tunnel barrier connects to a source electrode. The other tunnel barrier connects the dot to a drain electrode. Let's connect that up to physical reality. Here's the source that the electrons hop onto the dot from. Here's the drain that allows the electrons to get off the dot. So that's kind of our current path. Electrons are going to tunnel through this. And in terms of the physics, the key thing to keep in mind is that these are really small structures. So you think about a charging energy, like 1/2 CV squared, energy stored in a capacitor. The energy required to add or remove one electron from this dot goes like 1 over the dot capacitance. And you can plug in numbers, 4 pi epsilon naught r, and calculate the capacitance. For a 10, 20 nanometer scale dot, this capacitance is going to be on the order of 10 to the minus 18 farads. It's very small because it's a nanometer scale system. So now you calculate that charging energy for a typical dot size, and you can have charging energies, experimental measurements that are on the order of 5 or 10 millielectron volts. And if we're at 8 millikelvin, the thermal temperature is much, much less than a few millielectron volts. And so basically the charge number on this dot is frozen. It's quantized, and you can't change it unless you pay this energy cost, this charging energy. So to compensate for this charging energy, what we can do is we can change the gate voltage. We can change the voltage on one of these gates. For example, if I make this voltage more positive, then it's going to become more energetically favorable to add an electron to this dot. So we can add electrons to the dot, 1 electron at a time, by increasing the gate voltage. And they're going to be special gate voltage at which the energy of, say, an n electron charge state is degenerate with an n-1 or an n+1 electron charge state. And specifically at these gate voltages that are associated with the red dots in this picture, the electron number can change because we've used the gate voltage to compensate for this large charging energy. So here, I'm going to have charge transitions between n-1 charge state and n-2 charge state. The electron number is going to oscillate as a function of time as we add and remove the electron from the dot. So there's another way to look at the physics of a dot, and we'll use energy level diagrams like this throughout the lectures. But here's our source electrode. It's 2-dimensional. It's filled up with electrons up to the Fermi level. Here's the drain electrode. It's 2-dimensional. It's filled up with electrons to the Fermi level. And here's our quantum dot. Our quantum dot is 0D. So we have discrete particle in a box states, and I've drawn those here, with the solid lines running across. There's some orbital energy spacing that's just due to the confinement, calculating the particle in the box problem. And there's a charging energy, the cost that we need to pay to add or remove an electron. So what happens is if we make this gate voltage more positive, we'll actually pull these levels down. And every time one goes through resonance with the source and drain electrodes, we can have resonant tunneling onto the dot. So if you were to measure the conductance through this device as a function of the gate voltage, you would see oscillations. And these are called Coulomb blockade peaks in conductance. And these peaks in conductance basically correspond to conditions like this, where the energy of an n electron charge state is equivalent to n+1 or n-1 energy, right? And these were first measured at MIT a long time ago, some of the first experiments. This led to a Buckley Prize, I think, with Mark Kastner and a few others. All right. Instead of just measuring conductance, we can look at a nonlinear response as well. And so this is the Fermi level of the source. This is the Fermi level of the drain. Let's now hook source and drain up to a battery so that we can apply a bias voltage across the device, okay? So we've now turned on this battery, which gives us an energy difference between the chemical potential of the source and drain electrodes. This is the bias window just set by that voltage, okay? But what does this do? It kind of loosens up a very restricted condition for electronic tunneling. Now if I have an empty energy level anywhere between this energy and this energy, I'll have a current through the device because I can have downhill tunneling through the system. And so basically what you can imagine is measuring the conductance through this device as a function of the voltage here, the source drain voltage across the device. And what that does is it's going to open up this bias window. And every time the top of the chemical potential of the source electrode crosses an energy level in our system, there's going to be another state that we can tunnel into. And having access to that additional state gives us another path through which current can flow through the device, and we'll see a peak in conductance. So you can very nicely actually map out the density of states of the quantum dot by measuring the conductance through it as a function of the source drain bias voltage. It's like shining light through that vapor cell, on the introductory slide. We're looking at current flow instead of light flow, but you can basically map out these discrete electronic states. And this is some of my old data from when I was a PhD student, but these are quantum states in a gold nanoparticle where we can look at tunneling onto a gold nanoparticle, copper nanoparticle, and basically probe out the density of states. Some really beautiful data from Leo Coulomb, 1997. This is from the device. This is called the vertical quantum dot. And again, what they're doing is they're measuring the conductance, DIDD, in a color scale plot. So white is 0, no conductance, and red is high conductance, as a function of the source drain bias voltage, which basically shifts this energy level relative to this energy level. And on the vertical axis, they're changing the gate voltage, which shifts these energy levels up and down. And what you can see, it's quite striking data, is that down here in this large region of space, the conductance is 0. And if I just run up vertically through the plot, the conductance is 0, then there's a peak in conductance, then it's 0, and there's a peak, 0, another peak. So what happens if you take a vertical cut through these data, you'll basically see Coulomb blockade peaks like are shown in this Mark Kastner paper, okay? What else do you see that's kind of interesting? There are regions here through which the conductance is 0, but there's kind of a pattern. This has a large energy gap before we add the next electron. And then there's a small energy gap, a small energy gap, small energy gap, and then we add the 6th electron, and there's a bigger energy gap. So what they showed in these early Coulomb papers is that you've heard in chemistry of Hund's rules, how you add electrons to atoms and kind of fill the energy levels, is that you can actually resolve Hund's rules for these semiconductor quantum dot systems in cases where you have a nice spherically symmetric confinement potential, okay? So these energies here are called addition energies, and what these measurements do are basically measure the energy cost that's required to add one electron to the dot, then the next electron, then the next electron. This addition energy has a boring capacitive charging energy component to it, and it has an interesting quantum orbital excited state energy component to it. And so you actually measure both of those. And they showed that these orbital energies depended sensitively to the number of electrons. And so this is kind of a cute paper. This is Physics World. It's sort of a general physics journal where the Coulomb group, they made their own periodic table based on the number of electrons that they had in their dots, right? So here are the addition energies that are plotted as a function of electron number, and you can kind of see the shell filling. For the 2nd electron, there's a big addition energy. For the 6th electron, there's a big addition energy. So there's number 6, there's number 2, so on and so forth. So this is a TA, that's a Tarucha, and Coulomb, and other members of their team have their own artificial atoms named after them. Okay. So it's kind of fun. You can actually see these quantum states in a transport measurement, which I think is pretty cool. All right, how can we measure the number of electrons? Well, there are a couple ways to do it. Back in this early work, they changed this gate voltage. And this is making the gate voltage more negative, which is reducing the electron number from 6, 5, 4, 3, 2, 1, 0. And they see that as they go beyond this gate voltage, there's no more conductance. So their interpretation in these early experiments was, well, beyond this gate voltage, we push the last electron out, there are no more electrons to kick out of the dot, and so it's empty, and that's how they assign n equals 0. And I think these are pretty clear data, but there are other data sets where it's a little ambiguous. So another technique has been developed in our field to measure the absolute number of electrons on a quantum dot. And this is called single electron charge detection. And I just want to describe for you how it works, and then I'll show you some data from our group here. This is a single quantum dot that's defined with 4 gate electrodes. So the white circle is kind of denoting the quantum dot. And what's fabricated to the right of the quantum dot is a quantum point contact. It's a one-dimensional constriction that electrons are forced to tunnel through. You want to think about electronic devices? Think of a field effect transistor. A field effect transistor has a source and a drain and a gate. And if you change the voltage on a gate, you can turn the transistor on or off, right? This quantum point contact, very loosely is similar to a field effect transistor. It's sensitive to the local electrostatic environment. So this paper by Field, PRL from 1993, I think that was largely missed by the community. But what this group showed is that they could measure the conductance through the dot as a function of the gate voltage and observe these Coulomb blockade peaks, as we discussed before. But if they measured the conductance through this quantum point contact, they saw that every time the electron number changed on the dot, there was a change in the conductance through this quantum point contact. And the reason is, right, if I add an electron to the dot, it changes the local electrostatic environment near that quantum point contact, and it changes the conductance through it. So these little steps here that you see, the sawtooth pattern, that little blip there is the signal from one electron hopping off of the dot. You can actually resolve these single electron tunneling events through this conductance measurement, okay? And this is kind of a bulletproof measurement approach. Let's look at more recent data. This is from our group from last year. This is a 9-dot device. We have dots 1, 2, 3 up through number 9. And to measure the number of electrons in this spin chain of 9 dots, we have 3 charge detectors, okay? If we measure the conductance through this charge detector, we see a Coulomb blockade peak, okay? So that's the red curve here. And what we find is that if we change the number of electrons on dot number 8 from 0 to 1, there's a shift in the position of this Coulomb blockade peak. And that shift leads to a pretty measurable change in conductance. And so what we're doing directly is we're using one quantum dot as a local probe of the electrostatic environment to measure the number of electrons that are on other quantum dots in this chain, right? So that's a pretty big change in conductance here.
How do you calibrate the absolute to 0?
What we can do is we sweep this gate voltage over a large range.
Still no states.
That's right. And then eventually nothing changes. And at that point, you know that you've removed the last electron. Another way to look at it is you'll see the shell filling. So you start from where you think you have 0, you have the first, second, third, so on and so forth, and you measure those addition energies, and you can that's a further evidence, right, that you're really at n equals 0. So it's a combination of, I'd say, transport, shell filling, and charge sensing. Okay.
So there's a number of electrons in the conduction band. So there are field valence bands, right?
Yeah, so these are free electrons that are in this two-dimensional electron gas at this interface between, in this case, it's silicon and silicon germanium. Yeah. So now what we can do, we have the ability to actually detect when the electron number changes. This is kind of interesting. We can actually look at real-time tunneling of an electron now. So we can basically connect this quantum dot to a source or drain electrode and measure the current through the charge sensor as a function of time, okay? And so what you'd expect to see is if the gate voltage above the dot is here, the electron number is 1. If the gate voltage is down here, it's 0. But if I sit right at the transition between the 1 and 0 charge state, the electron number is going to fluctuate because we're coupling this discrete energy level to a Fermi sea. And the Fermi sea is broadened by KT, okay? So what we can do then is measure the statistics of the charge state. Up here, the quantum dot predominantly has 1 electron on it, and so the signal is high. Down here, the quantum dot's empty, and so the signal's low. Every now and then you see electron hop on and then hop back off. And if you sit right at the transition between n equals 1 and n equals 0, you'll see this random, it looks like telegraph signal noise. But really, this is a single electron hopping on and off, on and off. And now we can measure the statistics of these, measure the time average occupation of the dot as a function of gate voltage, just using these time series, and it fits perfectly to a Fermi function. From the width of this, we can extract, KT. So this shows that in the laboratory, right, we have the sensitivity to tell when the electron number on the dot changes by 1. Okay? That's what this signal is. That step is from 1 charge hopping off the dot there. All right. Can dig a little bit deeper and kind of ask, what's the signal to noise? So now let's take like a histogram of a really long time series. It's gonna have two peaks associated with 0 and 1 electron occupancy with some noise on top of it. And you can see that these are pretty well separated Gaussian peaks. And so we have a nice signal to noise. And from the measurement speed, you can convert this into a charge sensitivity. And we can measure a fraction of an electron in the laboratory easily, using this charge detection. And so this is work from our group, looking at qubits. There's other work by Klaus Edslund's group, a nice review article where they looked at full counting statistics of single electron transitions in these devices and backed out some nice information about spin and charge. So that's this paper here.
Can I understand it as the line width as the lifetime of the electron?
No, it's not. This is just a noise. Noise on the device. So there's noise here, right? This width here of the noise is about the width of this Gaussian. And then there's signal. I'm too short. The signal is from here to the dashed red line. That corresponds to this separation. I'll get David up here. I'm pointing at the board. All right, so that's what you're saying. It's not like a lifetime broadening from having excessive tunnel coupling to the leads. This is just measurement noise and noise on the device. It's a little bit more boring, but you care about this practically. What is your signal to noise and how easy is it to resolve these states? Okay, all right. We can access charge. We can tell when charge changes. How about spin? How can we access spin through quantum transport? Here's our picture of our discrete particle in a box states in the dot. Now let's add spin. And there's a model in quantum dots. It's called the constant interaction model. Constant interaction model says that you solve the Schrodinger equation for your quantum dot. You calculate what the energy eigenstates are. You have some ladder of states. And now you add electrons to it. So I put spin up, spin down in the lowest state, and then I move up an energy level, I add spin up, spin down, so on and so forth. And so you fill this ladder of states, and that's what I've done here in this picture. Spin up, spin down, 2 electrons per energy level. Okay, how do we access spin? So now we take this device, we put it in a large magnetic field, and the energy of the spin up and spin down states will increase the energy difference, the Zeeman splitting, and we can resolve that Zeeman splitting directly in a conductance measurement. Okay. So this is Zeeman splitting of these discrete particle in a box states as the Z component of the magnetic field is increased in a laboratory. Right? So you can now probe spin.
If we increase the magnetic field further, do we have level crossing or?
You'll actually have in this, you can see it here, there's a level anti-crossing between
So
the
they are
states.
like mixed.
Yeah, these are mixed in this material. This is actually it's not a gallium arsenide dot. This is a copper nanoparticle. It has pretty large spin orbit coupling. And the spin orbit coupling mixes the eigenstates and it gives you these avoid crossings.
Oh.
Yeah. But you're right, if we were to go higher, this is all we had in our lab at the time was 9 Tesla, but if we went higher, eventually the other states would merge and have avoided crossings. But this was, early physics quantum dot devices in the late 90s, 2000s, looking at level statistics and these avoided crossings and making comparisons with random matrix theory and other quantum theories. But that was a big part of mesoscopic physics 15 years ago. All right, so this is a nanoparticle. This is a gallium arsenide quantum dot. Another paper here from the Coulomb group. I showed this to you before, a single quantum dot, a charge detector. And what they did here was they measured the conductance through this device as a function of magnetic field. And so you can see here, it's not the cleanest data, but I think you can see it, that the level splitting at the ground state transition increases with magnetic field. And so this splitting here is just directly the Zeeman splitting. So they mapped out for the first time in a semiconductor quantum dot here, the electronic G factor basically by measuring the Zeeman splitting. Okay. So now we have access to spin. Once we have access to spin, we can dig in and think about making spin qubits. So what I'm going to do is walk you through, the DiVincenzo criteria. Hopefully you heard about these. And Steve, did you talk about these in your first lecture a little bit?
A little bit.
Just loosely.
Yeah.
Yeah. So we want to make a qubit. We need to be able to initialize it, read it out, perform some set of gates, build many of them, and ideally have a scalable system. And for semiconductor spin qubits, the kind of roadmap that was developed in the late 90s is what's called the lost DiVincenzo proposal. And basically what this means is, for these DiVincenzo criteria, we need a way of physically implementing each one. So for a spin, we need to initialize a spin, we need to read out spin, control single spins, couple spins together, and have some way to build this up into a large device. So what I want to do now, for the remaining parts of the lecture is kind of walk you through this set of requirements and tell you how this can be achieved in the laboratory. How can we initialize a spin qubit? Okay. Here's an energy level diagram for a single spin qubit. We're at a high magnetic field so that there's Zeeman splitting easy between the ground state and the excited state. And for simplicity, we're just going to consider coupling to one Fermi C on the source side. And imagine that I've made the tunnel barrier on the other side of the dot so high that it's really unlikely that an electron's going to hop out. This is just for simplicity. I want to take this system and initialize it in a well-defined spin state. So what we're going to do, this is important to recognize, these pieces of metal have voltages on them. The voltages don't necessarily need to be static, or tuned very slowly. We can tune them quite quickly in the laboratory using a pulse generator. And that pulse generator allows us to shift these energy levels around as a function of time, on a nanosecond or 100 picosecond time scale. What we're going to do is we're going to apply a voltage pulse to one of these gates, and we're going to shift these levels down in energy. And we're going to do it carefully, so that the energy of the spin-up electron is below the Fermi level of the lead, but the energy of the spin-down electron is above the Fermi level of the lead. And if we're at low temperatures, then I can only load an electron into the spin-up state. Okay, so this is how you initialize spin. And if you do this at low temperatures and high magnetic fields, it was shown by Atashi Namamoto's group that the error rate can be, quite small, a part in 10 to the 5 error rate. It's basically just a Boltzmann factor. So you work at high field, low temperatures, and this works pretty well. Okay, so that's spin initialization. If you had 5 spin qubits, you would just do this for each qubit. How do you control it and sort of do readout? For readout, you have to be clever because the magnetic moment for a single spin is very small. But I showed you already that we can measure charge routinely in this field using these charge detectors. We're going to use spin selection rules and charge conversion to read out spin states. So imagine we have the same system shown here. It's initialized in spin up, and now we drive the qubit. We drive rotations between spin up and spin down coherently. We turn off that pulse, and we want to do our measurement. We want to determine whether or not the electron is spin up or spin down at the end of the day. And the way that we do this is kind of the reverse of initialization. Okay? So it's a question mark. What state are we in? We want to do readout. What we're going to do now is we're going to take this system. I'm going to show 2 different cases. For final state spin up, and in a second I'll show you what happens if the final state is spin down. So imagine that we apply 2 pi pulses to the system, which basically brings us back to our initial state. Now we're going to shift the energy levels up in energy. And you can see that the energy of this spin up state is below the Fermi level of the lead. We're at low temperature, so there's no thermal excitation. We're not shining any radiation on the device. And this spin up electron is basically stuck in that level. So if you measure the charge detector, there's a charge detector next to your dot. You measure the charge on the dot, it doesn't change because that electron's stuck there, right? It hasn't hopped off. Let's contrast that with the spin down state. We do our experiment, we apply some Rabi pulse. This time it flips us from up to down. So our final state spin down. We want to do a measurement. We shift the energy level up. And now you can see that this spin down electron would like to hop off the dot into the Fermi C. And now what happens is you see that if you look at the charge detector, there's a change in the charge on the dot. Okay? So this is due to spin-dependent tunneling. Does everyone see it? So it's an energy selective tunneling process where we have Zeeman splitting, and if Zeeman's greater than KT, then all this works fine, right? It's okay? What else can go wrong? I mean, this is experimental physics. Temperature can be an issue, but what else can go wrong?
Tunneling?
What?
Tunneling?
Tunneling. So once this hops off, an electron can hop back into the lower state, right? And I need to be able to have sufficient measurement rate to see these transitions, right? Because if this hops off and it is immediately replaced by the other spin state, then I'm going to see a really short blip, and I might miss that blip if I don't look carefully enough. So that's great. There's one other thing that can go wrong. I mean, in the lab, there are a lot of things that can go wrong, but you know, look at this cartoon picture. There's another thing that can happen. Is the lifetime of this state infinite? At some point, this spin state can actually relax to the ground state through what's called the T1 process. Our qubits aren't perfect. They relax and they dephase. And if that relaxation rate is too fast, then we're going to have some false counts, because during our measurement, the spin can actually relax and we'll have an error. Right? So there are always limitations to our measurements that we do, and it's just important to understand what the limitations are. Okay? So these rates need to be tuned so that they're not like a gigahertz, because if they're a gigahertz and this hops out in a nanosecond, it's replaced with another electron in a nanosecond, and I can't measure that fast, right? But I don't want to make this so slow that the spin state relaxes. Right? So there's a fine kind of trade-off, practical considerations. How about spin control? For spin, what we want to do is we want to be able to rotate this block vector any different position on the block sphere. And the way that this is conventionally done with spin is using a process called electron spin resonance. So here are spin states. We have spin down and spin up, split by the Ezerman energy. And we want to make a coherent superposition of spin up and spin down. And in our quantum dot community, there are a few ways to do this, and I'll walk you through these now. First is what I call brute force electron spin resonance. There's another process called electric dipole spin resonance that uses spin orbit coupling to actually coherently control the spin state. And this is what we're using now downstairs. It works remarkably well. This is called slanting Ezerman field electron spin resonance. But it's a way of electrically driving a spin transition using a synthetic spin orbit field that's generated from the fringing field of a little micromagnet. Okay, it works really well. All right, brute force ESR. Why do I call it brute force? This is basically, you know, the Biot-Savart law from Physics 104. Right? You drive a current through a wire, that gives you a magnetic field, and we want to drive an AC magnetic field to drive a rotation between spin up and spin down. So this is an early experiment from the Delft group, where they took a quantum dot device. If you kind of peek here, you see the gate electrodes underneath. So they make their quantum dot, and then on top of it, they put a big microwave antenna. And they're going to drive a gigahertz frequency current through this that oscillates a magnetic field. Okay. And you can see here, there are driven oscillations in this device. This is a plot of the spin state probability as a function of the burst time of this microwave field. And they were able to resolve Rabi oscillations of a single spin. Another question for you. How could this be a problem in terms of scaling up? What kind of current do you need to generate a millitesla? Anyone know? Back of the envelope, I think the answer is here. So this is a few milliamps of current. That's fine at room temperature, but at 8 millikelvin, it's a problem, right? Because you don't have a lot of cooling power. And so one of the challenges with this is that first you need to get these antennas close to your device, and then there's just I squared R joule heating from passing milliamps of current through this device at millikelvin temperature. So this doesn't scale all that well. There are a few groups trying to do this, but you need to worry about just power dissipation when you're working at these low temperatures. So due to the challenges associated with this, the community's thought a bit about different ways to control spin degree of freedom. And this is a paper by Rashba from Rashba spin orbit coupling, where he suggests that it should be possible to electrically control the spin state of an electron using purely electric fields. And what we like about electric fields in terms of our computing architecture is that we have all these gates that define our quantum dot. The gate voltages can be static, but they can also be dynamic. And so it's easy for us to locally generate electric fields that don't dissipate a lot of energy, okay, just by applying an oscillating voltage to one of these gates. And so here's the physics. This is a general spin orbit coupling Hamiltonian. It basically says if we have an electron moving in space with some momentum p in the presence of an electric field, that electric field gets Lorentz converted into an effective magnetic field. And so you can use this effective magnetic field to drive your AC qubit oscillations. So the theory for quantum dots was worked out by Daniel Loss's group. There's also a paper by Karsten Flensburg here in strong spin orbit nanowire devices. But basically, you can write down an effective Hamiltonian where you take a single spin, put it in a large magnetic field, and this is just a static Zeeman term that splits spin up and spin down. And now what we're going to do is we're going to take our quantum dot, which gives us a parabolic electronic confinement potential. And instead of having this just be entirely static, we're going to oscillate the voltage on one of the quantum dot gates, and we're going to shift this wave packet back and forth as a function of time. But we're going to do it at the Larmor precession frequency of the single spin. We're going to drive the system on resonance and basically shake that electron. And what this shaking of the electron does in an electric field is it gives an effective magnetic field here that you can use to actually drive single spin resonance. So they wrote down an equation here for the effective Rabi frequency, and it depends on basic parameters like the strength of spin orbit coupling, the magnitude of the electric field in your system, and the tightness of this electronic confinement potential. You want to be able to push this by a significant amount to take advantage of spin orbit coupling. And a year or so later, this is another paper from the Delft group. These are single spin Rabi oscillations in gallium arsenide quantum dot that are driven purely using this electrical method. And it was really a tour de force experiment, but the kind of disappointment was that if you looked at the Rabi frequency that they had for their oscillations, it was a factor of 2 slower than the brute force, let's drive a current through a wire and rotate the spin kind of approach. And practically, we're always fighting decoherence and dephasing. And so we'd like to have these gate control times be as short as possible, right? We'd like to rotate the qubit really quickly compared to the dephasing rate. And so if you have a slower gate, it's kind of a problem. So what can you do? You can look at the periodic table and ask, all right, we'll typically work with gallium arsenide. What can we do to increase spin orbit coupling? I can go to heavier elements like indium arsenide or indium antimonide, where the spin orbit coupling is much larger, and you'd expect the Rabi frequency to scale up significantly. So a few years later, this is another paper from the Delft group. They made a spin qubit out of the indium arsenide nanowire, and they showed that the spin orbit coupling allows you to drive really fast. If you look at the scale here, these are 30, 40 megahertz Rabi frequencies for single spin, driven electrically. And so you can see that by changing materials, sometimes you can get around these kind of pesky problems in terms of quantum control. All right, so that's the electrical driving. But what else can you do? For ESR, you want a static magnetic field that gives Zeeman splitting and a large transverse oscillating magnetic field. Another way to obtain that large transverse field is to work in a system that has a large magnetic field gradient. And if you shake an electron in a system with a large magnetic field gradient, the Zeeman energy is going to depend on the position of that electron. And this is a proposal by Tarucha's group. Tokura suggested that instead of using boring gold gate electrodes to define our quantum dots, we might think of using magnetic gate electrodes. If you think about a bar magnet, it's magnetized, it has a fringing field near the end, and the fringing field gives you a very large field gradient. For a typical system, it might be a couple Gauss per nanometer kind of field scale. That gives a pretty large effective spin orbit coupling. So the picture is that you would have this magnetic gate, it gives you a magnetic field gradient, and then you shake your electron in this magnetic field gradient, and that gives you electron spin resonance. This was demonstrated by Tarucha's group. A few years later, they took a quantum dot device. You can see the gate electrodes here. And on top of the quantum dot, they put a little piece of cobalt down. It's a small piece of cobalt. Cobalt's like a bar magnet. It has a fringing field that wraps around it. And then they shook the electron in the presence of this fringing field and showed that they could drive electron spin resonance transitions. Just in the past year or two, this technique has been adapted to silicon quantum dots, which have much longer spin coherence times in comparison to the gallium arsenide system. And this has been a game changer for our community. If you look at these Rabi oscillations, right, this isn't a perfect sine wave, admittedly. There's a lot of damping, and that's just due to dephasing, spin dephasing. But in silicon, the coherence times are much longer, And now using this slanting Zeeman electron spin resonance, single spin rotation fidelities easily exceeding 99% have been demonstrated in silicon. So I think the single spin control problem, to a large extent, has been solved using this slanting Zeeman approach. Okay? So that's kind of good news. Let's talk about decoherence a little bit. You know, in terms of our quantum bits, we have a single electron. It's trapped in a quantum dot. It's sensitive to charge. There's charge dephasing. There's electron-phonon coupling. And there's spin orbit and hyperfine interactions. And all these interactions, right, lead to errors. And errors can be in the form of relaxation, energy relaxation between our two qubit states, or dephasing of our states. So let's talk about the basics of quantum dots and the different forms of relaxation. In our system, there can be charge relaxation processes where we have energy relaxation from some charge excited state to some ground state with no spin involved. This process generally occurs by spontaneous emission of a phonon on a very fast time scale, 10 nanoseconds typically, or shorter. Why work with spin? Spin is much less well coupled to the environment. If I want to flip this spin down electron to the ground state spin up, I need some mechanism that flips the spin and some mechanism that conserves energy when we have a transition from the excited state to the ground state. So instead of just having phonon emission, we need phonon emission plus spin orbit, or phonon emission plus hyperfine coupling to flip the spin and conserve energy. And so that leads to rates that are typically much, much slower, on the order of kilohertz. This is why we work with spin. So let's talk briefly about spin orbit coupling. I showed you this Hamiltonian earlier. In a two-dimensional electron gas system, there's a nice kind of intuitive picture for what spin orbit coupling looks like. Spin orbit coupling in a two-dimensional electron gas has two forms. There's something called the Rashba form and a Dresselhaus form. The Rashba term is due to electric fields at interfaces, say the interface between gallium arsenide and aluminum gallium arsenide. These materials have very large differences in their energy gaps. So there's a large step in the potential. There's a large electric field at the interface. And so if you have an electron moving around at that interface between gallium arsenide and aluminum gallium arsenide, it's going to experience a momentum-dependent magnetic field, and that's called the Rashba field, after Rashba. So look at this map, and what the arrows here show you is the effective magnetic field direction of an electron in the 2-deg as a function of its momentum. If it's moving to the right with positive momentum along the x-axis, it's going to experience an effective field that's down. If it's moving to the left, it experiences an effective magnetic field that's up. And so you have this momentum-dependent magnetic field that comes about due to spin orbit coupling. The Dresselhaus term is due to the fact that gallium arsenide, zinc blende crystal structure that lacks inversion symmetry. And so there's an internal crystal field that leads to its own spin orbit coupling, and it has this shape. If you kind of want to look at the physics, you can see that there are specific momenta, in the 2D plane where the Rashba and Dresselhaus fields can add up. And there are also momenta, like here, where they add up destructively and kind of cancel each other out. Okay? So the spin orbit coupling in these systems, kind of surprisingly, can be tuned quite a bit by tuning the Rashba field and looking at the interplay between the Rashba and the Dresselhaus terms. The other main term is a hyperfine coupling. I want to give you an intuitive picture for hyperfine coupling. We have an electron that's sitting in our dot, but this is an extended wave function, and this electron overlaps with about 1 million lattice nuclei. And in 3-5 semiconductors like gallium arsenide or indium arsenide, all of these lattice nuclei carry spin. And if you think about what the electron spin experiences, it experiences an effective field that's due to our superconducting magnet, but it also seals the local field generated by each one of these nuclei. And so I have a sum over about 1 million lattice nuclei that gives us an effective nuclear field or Oberhauser field. And this field can be big. If all these nuclei were polarized, we would have an effective Oberhauser field of about 5 Tesla. Even if there are random fluctuations in the orientation of these nuclei, there's going to be a root mean square field for gallium arsenide that's on the order of a couple millitesla. And so this will lead to pretty fast spin dephasing. So let's see how all this impacts the lifetime of our spin state. This is a single spin relaxation measurement. It's pretty famous. It was first demonstrated by Ezerman of the Delft group. It's one of the first measurements of single spin T1 in a semiconductor quantum dot. You've seen this before. This is the quantum dot. This is the charge detector. They measure the current through the charge detector to probe the number of electrons on the dot. And basically start off with the quantum dot's empty, and then they pull the energy levels down. They can either load a spin up or spin down electron, wait for some time here, and then measure whether or not the electron is in the spin up or spin down state after waiting, using this technique that we talked about before. So if the electron is spin down, it hops off and it's replaced by a spin up electron. If the electron is spin up, then nothing happens. And so they can distinguish between spin up and spin down by measuring the current through this charge detector. And what they found, and this is some of the first data, it was a little rough, but they measured the spin lifetime at 10 Tesla, and they showed us about 500 microseconds. That's short, compared to a second, but the charge relaxation times in these systems are usually like 1 to 10 nanoseconds. So this is significantly longer than you could have for charge, right? So the spin's long-lived. And then there were later follow-up experiments. This is a paper by Jonathan Finley's group in Germany, where they used an optical technique to measure the spin lifetime as a function of magnetic field. This is pretty clear data. Over a factor of 8 here in magnetic field, they found that the spin relaxation rate of a single electron scaled like b to the 5th. Okay? So there's very strong magnetic field dependence of the spin lifetime. Now, where does this come from? Well, it can either come from spin orbit plus phonons or hyperfine plus phonons. And Daniel Loss's group, and as well as Erlingson, Nazarov, and Falco in this PRV, looked at this mechanism. And it's kind of a nice Fermi golden rule argument for why you'd expect a rate that goes like b to the 5th. So the first thing is that when the spin relaxes from the excited state to the ground state, we need to conserve energy. Energy is conserved by emitting a phonon, a lattice vibration. So we're sensitive to the phonon density of states. That goes like the Zeeman energy squared. And then we're looking at a spin transition matrix element between spin up and spin down. This is sensitive to spin orbit coupling. So there's a term that goes like the Zeeman energy, and it also is dependent on electron-phonon coupling. So how does the electron-phonon coupling work out? In these systems, there are two different electron-phonon coupling mechanisms. One's called piezoelectric, due to the fact that it's gallium arsenide and there's a crystal field that can be changed with strain. Another term is what's called deformation potential, that if you strain a crystal, you'll push the conduction band around. And piezoelectric interaction dominates in the system, so you have a term that goes like 1 over Zeeman energy to the 1/2. And if you lump all this together, you can show from this Fermi's golden rule argument that the rate should go like b to the 5th. And that's really what's seen, quite nicely in these experiments. Here's another way to look at it. Here's our dot. This length scale is 20 or 30 nanometers. Think about a phonon as a lattice vibration. It can have a long wavelength or a short wavelength. If the wavelength is long, the dot just kind of rides up and down slowly on this oscillating potential, right? It doesn't see much. If the wavelength is really, really short compared to the dot size, then the quantum dot just averages over all these rapid oscillations and is unaffected. But if the dot size is comparable to this wavelength, then you'll sort of have maximal coupling. And this is a later paper, again by the Delft group, where they measured the relaxation rate as a function of, in this case, it was singlet triplet splitting, and showed a non-monotonic dependence of the relaxation rate that they linked up to this kind of self-averaging over the crystal field. Okay, so I think the main take-home message is if you look at the physics of our system, the relaxation process is really well understood at this stage. I think there are no major open questions in terms of single spin T1 in these systems. So I just have about 10 minutes left for this first lecture, and then we'll take a break. So I want to make a transition, describes changing material systems. So one of the things that we've done recently in our group is move to silicon instead of 3.5s. And reasons for this are kind of twofold. One is that you can make a lot of silicon transistors on a chip, just using standard fabrication processes. Another thing that we've learned, through measurements as well as theory, is that the spin decoherence rate, basically, the spin dephasing time gets longer and longer as you go to higher and higher purity systems, right? And so silicon can be purified at a very high level chemically. In contrast to the 3-5 semiconductors, it can also be purified isotopically to get rid of spin-carrying silicon-29 nuclei. And this is a prediction from Shankar Sharma's group that shows the expected decoherence time, T2, for a spin in a semiconductor material, silicon, as a function of the silicon-29 concentration. Okay, so this is sort of natural abundance out here, and it's your Avogadro material, Steve, like 500 ppm, so it's somewhere in here, right? So if you go to isotopically enriched silicon, right, you can expect to have very long coherence times. And this has actually been borne out in an experiment. Steve might talk about these measurements, but these are bulk electron spin resonance measurements from Steve's group here at Princeton by Alexei Tereshkin, showing coherence times in silicon that are on the order of tens of seconds. It's also another pretty powerful experiment by Mike Thewald's group. And what they showed is that they could basically have a phosphorus doped silicon that has an electronic degree of freedom and a nuclear spin degree of freedom of the donor. They showed that they could transfer a quantum coherence to the nuclear spin system and basically warm the sample up to room temperature. They let it sit there for like 40 minutes and cool it back down and did an optical measurement. And they showed that they could have basically a room temperature quantum memory with a lifetime that was 40 minutes, right? So this is really significant. In the late 1990s, in the first superconducting qubit experiments, in the first semiconductor quantum dot experiments, we only had coherence times that were like a nanosecond. You could see 1 or 2 Rabi oscillations and then everything just flew apart, right, due to rapid dephasing. But in these systems now, in silicon, can have these extremely long coherence times. And what we're trying to do in my group is probe spin coherence in silicon at the single electron level, okay, with 1 electron and a dot. So now I'll get back to your question earlier about that picture. Okay? So what we're working now is we're using silicon germanium heterostructures, and this is a transmission electron microscope image of what our heterostructure looks like. It's basically a silicon quantum well that we're going to trap the electrons in, sort of our 2D electron gas, if you want to think it that way. And there's some trade-offs in moving from 3-5s to silicon. One is the effective mass. The effective mass of electrons in silicon is about 4 times higher than in gallium arsenide. And so if we want to trap a single electron in silicon, we need to make really tiny devices. And this is what our device structure looks like now. This is a 12 quantum dot device. What you're looking at are gate electrodes that are stacked on top of each other. And this gives us full control over the surface potential in this device and allows us to have really tight electronic confinement and an approach that, at least in one dimension, is pretty scalable. We can make a spin chain now that has 9 dots that are basically connected up in series. So this is what the gate pattern looks like. I showed this before. This is a simulation. It's not data. Simulation of the electronic density in the silicon quantum well as a function of the 2D position underneath these gates. So you can see the 9 dots, 1, 2, 3 through 9, and then these are our charge detectors. This is an old-fashioned gallium arsenide device from about 2005, shown on the same scale bar. This was a double dot with a single charge sensor, and now you can see we have 9 dots and 3 charge sensors basically in the same area, and that's the effective mass. And we need to make much smaller samples in silicon if we want to be successful. Let's look at the qubit control. We take this device, and now what we're doing in these data is we're putting a micromagnet on top of the chip, and we're using the slanting Zeeman approach for electron spin resonance. These are Rabi oscillations of a single spin. We're measuring the spin-up probability of an electron as a function of the microwave burst length and as a function of the frequency of the microwave diode. These are typically called Rabi chevron patterns. And what we see in silicon is we can do something that's called randomized benchmarking, and we can measure the error per gate. After we perform many consecutive rotations on the single spin, we can see how the errors add up. It's called randomized benchmarking, and we now have error rates that are less than 1%. So we have 99.7% fidelity for this particular spin. And these are the time domain Rabi oscillations. And this is actually natural silicon. If we go to isotopically enriched silicon, this will even be better. In addition to single spin control, we need a way to couple individual spins together. And what we've been able to do in this work just since March this year is show that we can turn on and off an exchange coupling between two spins in this spin chain device. And what the exchange coupling does is it basically tells us that the energy of the left dot spin is going to be dependent on whether or not the right dot spin is in the down state or in the up state. And we can measure this exchange splitting spectroscopically by basically probing the electron spin resonance transition of the left spin as a function of frequency here. As we vary the voltage on the gate that separates the left spin from the right spin, okay? So if we pull this barrier down, there's a lot of wave function overlap and the exchange turns on. The barrier gate is high, then there's no wave function overlap and the exchange coupling is 0. So by tuning this gate, you can see that we start with a really small exchange splitting. As we make this gate more positive, the exchange splitting increases and we can have exchange splittings that are easily on the order of 10 megahertz in this device. This is a gate voltage tunable nearest neighbor exchange coupling, really between just two spins on a chip. Once we have the exchange coupling under control, we can kind of use it in a nice way to implement a C-naught gate for two spins in a single step. And the way this pull sequence works is we can do some pre-rotations on our two qubits. These are the rotation angles. And then we turn on the exchange coupling. And this plot shows the energy level diagram with exchange equals 0 and exchange not 0. Turning on the exchange splitting basically gives us a state-dependent ESR transition that we can drive. And in a single step, if we hit this transition, we can implement a C-naught gate. And so these are correlated 2-qubit coherent oscillations. And they're showing high fidelity 2-qubit gates in the silicon device. And we can implement now a C-naught gate in silicon in under 200 nanoseconds, okay, using time-dependent control of this exchange coupling. And so now we have single spin control and the two spin exchange coupling control in silicon devices, and we'll be continuing to push, over the next few years to other multiple qubit operations in silicon. So just to summarize here, I hope you've learned a bit about dots. The systems that we work with in the laboratory, in many ways are like artificial atoms. We can isolate single electrons using something called Coulomb blockade, measure electron occupancy through a variety of approaches, charge transport, charge sensing, measure spin state spectroscopically, initialize and read out spins. And hopefully these slides here, this is just submitted earlier this week, kind of show you state of the art. These are single spin rotations in silicon, very high fidelity. And also we now have nice 2-qubit control in silicon. So thanks for your attention. Are there any questions?
Maybe I have missed your point. You mentioned like the T1 relaxation time is about 10 nanoseconds. Then why T2 can be that long? I suppose T2 is limited by T1.
All right, so there are a couple of things to, I'd say, be a little careful about. For the T1, there are two different T1s in our system. There's a charged T1 time. Just imagine I get rid of spin altogether and I just have an orbital excited state with spin up and a orbital ground state with spin up, and the spin doesn't change, and I just look at relaxation. That's fast. That's about a 10 nanosecond relaxation time just for charge. When you add on spin, you need to lose that energy into the phonon, but also flip the spin due to spin orbit coupling. And this leads to a lifetime that's much longer.
I see.
Yeah.
So the transition element of the Fermi-Goldner rule is suppressed by the spin part.
Yeah, that's right. And just to go through it again, that's this physics here.
Yeah.
The phonon density of states in this matrix element squared. You kind of calculate this. This goes like b to the 5th. And so, again, we kind of need to be careful. If we're at really high magnetic fields, spin lifetime's not that long. Here it's 100 microseconds. But if we're at a Tesla, it's where we're at in the lab right now, is half a Tesla. You can have T1s that approach a second easily, or exceed seconds. So it's magnetic field dependent, and you kind of need to ask yourself where you're at in this diagram. Right, so you can have very long spin T2s in silicon because this T1 is so long. In many superconducting qubit implementations, the coherence time is limited by the lifetime. And that is maybe only 50 microseconds on a good day. All right, so that's kind of the best you can do. Any other questions? Yes?
So if I hear about like, state-of-the-art best miniature quantum computers we have,
Yeah.
I usually hear about something like 5-ish qubit computers with trapped ions. What's stopping this from competing, quantum dots from competing with that? Or am I just listening to the wrong guys, or what's?
Yeah, I think the main challenge for us has been decoherence, that a lot of the early work was done in gallium arsenide because you had access to very high quality two-dimensional electron gas and could do these sort of single qubit experiments. But the spin dephasing times were so short that when Tarucha group and other groups tried to implement a C naught in gallium arsenide, you would maybe see a 15% change, like visibility in terms of the quantum state mechanism. So if you try to do a 4-qubit experiment where your 2-qubit barely works, right, you're just basically shut down. And that's where we were at for, I'd say, the past 5 or 6 years. But now in silicon, we have this isotopic enrichment, which is very good in terms of coherence. And a lot of what our group has been battling are materials challenges and fabrication challenges because there's no Lauren Pfeiffer, for silicon. There's like no well-developed MBE growth process for these silicon germanium quantum wells. And we had to work that out, and that takes time. But now that the quantum wells work, and we have these new gate designs, it looks quite good in terms of single qubit and 2-qubit gates, right? So we have nice control, but all this is very recent, and we'll have to see how far we can push it. So we're gearing up in the lab now for a 4-qubit experiment, and then we'll go from there. But I think to a large extent, we've kind of powered through some of the biggest challenges. The effective mass is one, is that our dots needed to be made really small, otherwise they didn't work well.
So did I get the numbers right that it looks like you can fit maybe 10 to the 5 or 10 to the 6 gates within a lifetime?
Yeah,
Of your-
easy.
That's really cool.
Yeah.
So,
Yep. Another thing that's been worrisome is selectivity.
Mhm.
Say you have 9 spins, and you want to rotate, you want to apply unitary to 1 without doing anything to the other 8. If they all have the same G factor and the same Zeeman splitting, and you apply a global electron spin resonance field, then you're just going to rotate all the spins, right? That's a problem. But what these micromagnets do, they give us a local field gradient that we can use for electrical Rabi oscillations, but they also give distinct Zeeman energies. Over 100 nanometer distance, the field changes significantly due to this magnetic field gradient. And so our electron spin resonance transitions now in this device are separated by 200 megahertz in frequency, and the ESR line width is only a megahertz. So you kind of have this very narrow comb of ESR transitions that we can hit selectively. That's also important. And before we didn't really have that. With the current carrying wire approach, that just gave you kind of a uniform AC magnetic field, but no DC field gradient. So a lot of different things that have come together just in the past couple of years that I think are pretty encouraging. Yeah. Any other questions? All right.
Actually, I have one
Yeah,
more.
sure.
Are you stuck to these Electron 1D chains with any with current proposals?
How good are you at fabrication? We're hiring. I'll make the advertisement now. I mean, a lot of it is how do you get the wires in.
Okay.
And the field has sort of been stuck at 2 and 3 dots. And last year, a student of mine, David Zajac, decided to be bold to try to make this 9-dot spin chain and kind of break out of that mold. So I'm pretty confident now with 1D, we can take it pretty far. And for the next couple of years, I think 9 dots will keep us busy. But then 2D, it depends on array size. I think that today we could do a 2x2 array, wouldn't be a problem. And maybe in the long run, a 4x4 array. But the big issue is how do you get wires in to something this small? They need to overlap and have multiple layers. So in parallel to all this device physics that we're working through, there's actually quite a bit of engineering going on of what are called flip chip processes, where you sort of try to get out of 2D and work on 3D, just so you can get all the wires out. And that's something that we're looking into now. But right now it's just 1D, but I think that it's technical issues that are stopping us from doing 2D. Any other questions?
Trouble getting silicon-28?
Silicon-28 is a problem. I think, I mean, I can tell you funny stories over coffee, but when I started here as an assistant professor, I reached out to some Russians to try to get some silicon-28, and they wanted to bring it over on a boat, and it was quite complicated. So I think the FBI got a little nervous about having silane shipped to. Silane's very toxic, it turns out. You know, so that's kind of the main challenge, Phil, is that the only silicon-28, at least that I know of, has come through Russian centrifuges. And so if you want to get access to it, you have to sometimes work with some shady characters. But there's a little bit around, and I think that there's a chance that possibly in the US, they'll restart some of the isotopic purification efforts to increase the material supply. But there's enough left now for maybe a couple of years, and Steve has little pieces of it. But for our devices, we really need the silicon-28 in a gas form so that we can do the CVD growth, and that just complicates things, you know, even worse. I mean, having solid silicon-28, it's not a problem, but we want silane, which is extremely toxic, right? And it needs to be isotopically enriched silicon-28, and so that's something we're working on. But it's a good point, and we do have silicon-28 quantum models, Phil, and we're making devices on them now. Any other questions?
Is silane just silicon gas?
It is. It's very toxic. So if you
Explosive.
and explosive, pyrophoric. There's something called LD50, which is like the lethal concentration. Now, if you give rats something that's toxic, and the LD50 level is like 1 kilogram, it means if you feed a rat 1 kilogram of that chemical, 50% of them are going to die. And for silane, the LD50 level, it's like part per billion concentration. So it's really, really bad stuff. Let's end on that note before we go eat some food, right? All right, so let's pick up in about 15 minutes.
Yeah, the silicon-28 story